Hey everyone, welcome back, and today let's solve Leetcode problem 322 titled Coin Change. So we're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. So we have to return the fewest number of coins that we need to make up that amount. And if that amount of money cannot be made up by any combination or grouping of the number of coins in our array, then we can return -1. And we may assume that we have an infinite number of each kind of coin, which is a very important constraint, because if we did not have that line of constraint, whenever the sum of our coins array would be strictly less than the amount input or parameter, then we know that we could never form that amount, and so we'd automatically output -1. But in this case, since we have an infinite number of each kind of coin, we can use however many coin we like to actually form that number optimally. So in example 1, we have the input array coins to be 1, 2, 5, and this is essentially saying that we have 3 different coins. The first coin is going to have a value of 1, the second to be a value of 2, and the third to be a value of 5, and our amount parameter is going to be $11 or cents, however you guys would like to interpret it for the unit. And we would output 3 because the fewest number of coins we'd actually need in this array to actually build that amount of 11 would be 2 5s and a 1, which is 3 different coins that do actually sum up to a value of 11, and so we'd output 3. So in example 2, we have coins to be an array of length 1, so we only have one different type of coin, and that's going to have a value of 2. And since our amount is 3 and the only type of coin we can actually form has a value of 2, since 3 isn't a multiple of 2, we'd output -1 because there's no way we can form $3 with only 2 cents or $2 value coins. So we'd output -1 because, of course, we can't actually make a formation or grouping of different coins to form that amount. And in example 3, we have coins to be an array of length 1, again, to be just 1. But in this case, our amount is 0, and so we'd output 0 because we don't actually need any coins to form no amount, right? Okay, so with that out of the way, I'll give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so if you guys haven't noticed yet, basically to solve this problem, we'll basically be using the dynamic programming algorithm. And the idea here is basically to build a solution by finding the minimum number of coins required for all amounts from 0 all the way up until that target amount. Okay? So to do this, we'll use a list or an array for any of you C++ or Java users called DP, where DP at indice I holds the minimum number of coins needed to make the amount I. And the size of the list will be the amount plus 1 because we also need to account for the base case of when amount is equal to 0, right? As I saw in example 3, when amount is 0, we'd always output 0 regardless of what our coins array is because we don't need any coins to make up no money, okay? Well, yeah, like I said, we'll initialize DP at index 0 to be 0 because, again, no coins are needed to make an amount of 0. And for all the other values in the list, we'll initialize them to be the infinity, or basically float of infinity in Python, because we haven't yet calculated the minimum number of coins for those amounts until we actually traverse through the coins array. And this is how that's going to be structured. So to actually initialize that DP array, I'm literally just going to call it DP, an alias or a short form of dynamic programming. And I'm going to set it equal to an array of basically the float of infinity, right? So this is basically the largest or most maximized value that you can get in Python. You could really just do like whatever value you like, whatever the math dot. I think for Java it's like math dot max int or something like that for any of you Java users. I'm not 100% sure, but that's how it is in Python, simply setting it to the floating point value of infinity. And so we'll set the floating point value of infinity for basically every single amount there is, plus 1. Okay? So again, what this does is we're initializing that array DP of size amount plus 1 because we need to handle amounts from 0 up until amount. Not from 1 till amount, but 0 until amount. And so we'll initialize all these values in DP to be infinity, or in this case, again, the float of infinity with strings in Python, because initially we'll assume that we cannot make any of these amounts, and we'll maximize it to be the worst case possible, and we can minimize and optimize from there as we actually traverse through the coins array. So once we initialize that DP array, Now we have to actually account for our base case, where our base case is essentially when we have an amount of 0, we don't need any coins to make up that amount, and so we'll set dp at index 0 when the amount is equal to 0 to be 0, because we don't need any coins to make $0, right? And because, yeah, for that reason. So now let's actually traverse through every single coin in the coins array, and we'll do this in Python like for coin in coins. And again, coin does not have to be your iterator. It can be really whatever you like as long as it's not a keyword in Python. I'm just going to call it coin because that's the most simple and understandable iterator that there is in this problem, in my opinion. So again, we're basically initializing a loop that goes through each coin in the coins list or array. And this allows us to check how each coin can actually help build the solution and update our indices I for the DP array to optimize how many coins we actually need to actually build that amount. So once I actually loop through all the different denominations of coins in the coins array, I'll actually have a nested loop to look through the range of the coin that we're looking at in this iteration up until the amount. And of course, in for loops here, the amount or your second parameter would be actually exclusive. And so to actually account for the amount as well in this loop or this range, I'll actually have to say amount plus 1, because this literally just loops through the range of values from the coin up until the amount plus 1 exclusive, or basically the amount inclusive, because we all want to actually include the amount as well. Okay? And again, what this does is for each coin, we'll loop through the amounts from the value of the coin itself, or basically the coin, up until that amount. And this ensures that we're only considering amounts that can be created using that coin, which is very important in this for loop. So for every single value or I in the range from this coin up until the amount or the parameter amount, we'll basically set dp at that index I for this iteration to be the minimum value or the most optimized way of course, dp at I, because we don't want to make dp at I smaller, the minimum of that or itself, and dp at I minus coin plus 1. And this is the very key crucial line, because we have to do this for every iteration to minimize or optimize every single indice for that specific coin value. Okay? So what this does is basically for each amount I, we're going to update dp at index I by taking the minimum of its current value, or basically dp at I, and the value dp at I minus coin plus 1. And the logic really is here is that if we can make the amount I minus coin, then we can add one more coin to make the amount I, okay? And we'll update our dp at index I for that iteration like so. And actually, once I'm done with this for loop here, I can actually exit this nested loop, and I can simply return dp at amount. But there again is another issue here. If dp amount is equal to the float of infinity, basically meaning that if we didn't find a more optimized or minimized solution to actually form the amount using the coins of different denominations that we actually had within our input coins, then we'd actually have to return -1 as basically our second base case. So the way I'm going to structure this in Python is return dp at index amount if dp at index amount isn't equal to the floating point of infinity. Basically what it was initialized to. And if it is, or basically the else statement here, if that's not the case, then we can simply return -1, just like how the problem wants us to. And so unless I made any syntax errors here, they should be submitted and they should be accepted. Okay, let's see what I did wrong here. Okay, yeah. As you guys can see, I'm pretty bad at actually like getting the right syntax here. Okay, yeah, this should actually be a tuple. This should not be just regular value by itself, because the Python wouldn't know what to actually multiply the float of infinity array by what, because this actually has to be a tuple or whatever iterable I can have to actually multiply an array by that value. So yeah, if you guys enjoyed that solution, please consider liking this video and subscribing to my channel. And as you guys can see, this is actually just about as efficient as you can get, beating 61.64% of users runtime complexity-wise and 80% of users memory complexity-wise. Okay. So to better explain the overall code functionality, because I understand that dynamic programming can be difficult, and this is a pretty hard problem to actually digest. Essentially, the code uses this dynamic programming to build a solution incrementally, right? So it starts by assuming that no amount can be made, basically setting everything or initializing everything to be infinity. and then it gradually fills the DP array by checking how each coin can contribute to making various amounts, okay? And so the main idea here in this code is that for every amount, we'll check if it can actually reach by adding one more coin to a smaller amount that we already know how to make. And by the end, the DP array will have stored the minimum number of coins needed for every amount from 0 to amount within those indices I. So for the time complexity here, this is going to be big O of n times n, where n is the number of coins and m is the target amount, and that's really because we iterate through each coin, and for each coin, we'll loop through all of the amounts from coin till amount. And for the space complexity here, this is going to be big O of m, where m is just the target amount, since we're really only using a list of size amount plus 1, or m plus 1, to store our solutions. So yeah, that's basically it for this dynamic programming problem. And if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel once again. And without further ado, I will see you guys in the next video. Bye-bye.